Charge Tape by Alan Zhu. Introduction. The purpose of this experiment is to familiarize the student with the idea of charges via experimenting with charged pieces of tape and observing their interactions with gravity and other pieces of charged tape to extract information about the charge of the tape. Here are some meta information about the experiment. The length of the tape was approximately 8 inches, which comes out to 0.2032 meters. The mass of the tape, following 1 gram per meter, is equal to 0.001 kg times 0.2032 meters, which comes out to approximately 2 times 10 to the negative 4. The distance between the two tapes during the float was 1 centimeter, which is approximately 0.01 meters. The magnitude of the gravitational force acting on the tape is equal to m times g, which, as you can see when plugged in the values, is approximately 0.002. The magnitude of the electric force acting on the tape should be the same as the magnitude of the gravitational force. This is because, in order to maintain float, the net force on the tape should be zero. So Fe is equal to approximately 0.002 as well.
The left is the flow experiment, where the tape is taped between a cup and another cup, and the right is the creation of the charged tapes. In this photo, the system is the tape, and the cups and gravity and everything else are the surroundings. Here is how I calculated.
Fe, as previously stated in the previous slides, is approximately equal to 0.002, and d, the distance between the two tapes during the float, was 0.01. K, in this example, is Coulomb's constant, which is 9e9. A formula for electric force is equal to E1 times K times E2 over d squared. Since it is assumed that E1 equals E2 in the PDF, Fe can be simplified to K times E2 squared over d squared. Using simple algebra, we can isolate E2. E2 equals the square root of Fe times d squared over K, which when you plug in comes out to approximately 4.7 times 10 to the negative 9 coulombs. Here are some relevant questions that I found in the PDF. The number of electrons was approximately 2.9 times 10 to the power of 10. This was calculated via taking the total charge and dividing over the charge of one electron. The electric tape was negatively charged and repelled other negatively charged objects, but attracted neutral objects and positive objects. Coding Part 1. When evaluating the single point charges, the charge came out to approximately 4.7 times 10 to the negative 9, as previously calculated by hand. This was not exact, but close enough. Here is my code for part 1. This is the creation of the two tapes, and this is establishing the mass of tape A. Here is my function for E field calculation, and here's my function for G-force calculation. This portion of the code represents how I calculated the net force. Here, I take the magnitude of the G-force, and here I am taking the magnitude of the electrical force, and I'm adding them together to get the net force. In the model, you can see two particles, the top one representing the top tape and the bottom one representing the bottom tape. The blue arrow represents magnitude of gravity pointing downwards, and the red arrow represents the force of electricity due to the red particle. Code Part 2. For a line of charge, the magnitude of the charge on a piece of tape came out to approximately 1.04548 times 10 to the negative 8 coulombs. The assumption here is that there are a total of 5 charges along the top and bottom tape. Here is my code for part 2, where I plug in the mass and I plug in a charge estimation. Here is my E-field function from the previous coding part. As you can see here, I changed the position vectors to represent what the vectors look like in real life. I also kept n equal to 5 to represent 5 charges along the top and bottom tape. I set the scales appropriately. When you run the program, you get something like this. As you can see, the charge that I inputted is almost equal to the gravitational force. What if? What if the charges of electrons and protons were swapped? What would change in our observation? Assuming the hand remains positively charged, the charge tape would repel rather than attract, since two positives would repel.
What would remain constant in observation? The two charged tapes would still repel, since they are alike, and the number of electrons/protons to maintain float would remain the same. Also, the charged tape and the neutral objects would still remain attracted.
Why are the required charges for the coding portion part 1 and part 2 different? The two models represent different models, the first one being a single charge model and the latter representing a line of charges. Since the line of charges is distributed throughout the entire tape, the latter model requires a stronger charge to maintain flow. The line of charges model is more akin to what the real value is because it isn't likely that the 8 inches of tape is represented by one singular charge. It would more so be a distributed charge